Good day and welcome to Math 111H Calculus 1 Honors, The Joys of X. On today's show we're going to discuss implicit differentiation. Suppose we cannot write y nicely or easily as a function of x, or if the curve does not represent a function, but only a function if divided into pieces. For example, we have this nice rose, three-leafed rose. This is clearly not a function. However, if we consider the curve in certain regions, for example, the region in the first quadrant where I'm pointing, in this region the curve is a function, and so we ought to be able to find the slope of the function at least in this region, and we can do that region by region by using the technique called implicit differentiation. So let's consider an example. Suppose we can write a curve in terms of x and y, but not necessarily solve for y as a function of x. For example, if we have x cubed plus y cubed equals 6xy. So what we do is we consider y to be a function of x in the region of interest. So every time we have a y, we can write it as y of x. So we get x cubed plus y of x cubed is equal to 6x times y of x. We can take the derivative of both sides using the chain rule and other differentiation rules, giving us the derivative of x cubed being 3x squared. Derivative of y cubed as a function of x using the chain rule is 3y squared times dy dx. And then we use product rule on the right. 6x times the derivative of y of x plus y of x times the derivative of 6x, which is just 6. So we get 3x squared plus 3y squared times dy dx is equal to 6x times dy dx plus 6 times y of x. We simplify grouping the dy dx's on one side and all the other terms on the other side, factor out the dy dx and divide by the 3y squared minus 6x, and we find dy dx is 6y minus 3x squared over 3y squared minus 6x, and we can divide everything by 3, giving us dy dx is 2y minus x squared divided by y squared minus 2x. We can also use implicit differentiation to find the derivative of the inverse trigonometric functions. Let's consider the case of y equals arc sine x. Well, we can operate on both sides with sine. So on the left we get sine of y, on the right we get sine of arc sine of x, which is just x in the appropriate region. Once again, we write y as y of x. So we have sine of y of x is equal to x. Taking the derivative on the left, we have derivative of sine of y is cosine y, and by the chain rule we need a dy dx. Derivative of x is 1. So we solve for dy dx. dy dx is 1 divided by cosine of y. We note that since sine squared plus cosine squared is 1, that cosine of y is the square root of 1 minus sine squared of y. So we have 1 over cosine y is equal to 1 over the square root of 1 minus sine squared y. And we note that sine of y is equal to x. So that gives us just 1 over the square root of 1 minus x squared. Another application of implicit differentiation is to find the derivative of x to a fractional power. Consider that m and n are whole numbers. If y is equal to m over n, we can raise both sides to the nth power, giving us on the left y to the n, on the right x to the m over n to the n, which is just x to the m. So we have y to the n is equal to x to the m. Once again, we note that y is a function of x, so we have y to the n of x is equal to x to the m. And taking derivatives on both sides gives us n times y to the n minus 1 of x times dy dx is m times x to the m minus 1, because we know how to take derivatives of y equals x to whole number powers. Okay, now it's just a matter of algebra. We solve for dy dx, giving us m divided by n. We have x to the m minus 1, and we need to divide by the y to the n minus 1. We would like to have our derivative of y be expressed only in terms of x, so we need to manipulate a little bit. We keep our m over n. We have x to the m minus 1. We'll multiply the numerator and denominator by y, and we'll keep the y to the n minus 1. This gives us in the denominator y to the n, but we know y to the n is x to the m. So the denominator just becomes n times x to the m, leaving the numerator alone. Okay, x to the m minus 1 over x to the m, that leaves 1x in the denominator. So we have m over n times y, and we have an x in the denominator. And y is equal to x to the m over n. So we just plug that into the numerator. We have x to the m over n over x. That's x to the m over n minus 1. So we have the derivative of y equals x to the fractional power m over n is m over n, x to the m over n minus 1. Our old favorite derivative works for x to whole numbers, and now we know it works for x to fractional powers. Okay, let's take a moment for math culture. There was an engineer, a physicist, and a mathematician who were driving through the desert when their car broke down. They pull over, and after examining the engine, they determined that there's only one thing they can do, and that is to walk to the nearest town. Since the walk might take them a long time, each of them decides to take something with him. The physicist takes a bag, the engineer takes a jug, and the mathematician unscrews one of the car doors. After walking a while, the physicist asks the engineer, "Why are you carrying the jug?" The engineer replies, "I say it contains water in case we get thirsty." The physicist and the mathematician agree that that's a great idea, and the engineer was smart to think of that in the desert. After walking some more, the engineer turns to the physicist and asks, "Why are you carrying the bag?" The physicist replies, "The bag has food in it, in case we get hungry." The engineer and the mathematician agree that that's a great idea, since it's likely that they won't get a meal for some time. After an even longer time, the engineer and the physicist turn curiously to the mathematician and ask, "Why are you carrying the car door?" The mathematician replies, "That way I can roll down the window in case it gets too hot." Thank you for joining us today. Have a great day, and may the power of math be with you.